limit of a function. So let's consider the function f of x equal x squared minus x plus 2 when x is near 2. We can calculate this limit by trying to see if we can estimate, trying to calculate what are the value of f of x at x is near 2. At x equal 1.8, f of x is, and you can calculate this on your own and fill this table in. So as you can see that when x is going to be very close to 2, the value of f of x is approaches 4. So what is the value of x as x approaches 2? F of x approaches 4. We express this by saying the limit of the function f of x equal x squared minus x plus 2 at x approaches 2 is equal to 4. And the notation for this is the limit as x approaches 2 of this function equal to 4. Now this has nothing to do with the value of the function at 2, right? The value of the function as 2 may or may not exist. Here we only talk about what the value of the function when it is near that point, when it's near or approaches that point. Okay, so let's take a look at this. How does the function f of x equal x squared minus 9 divided by x minus 3 behave near x equal 3? So as you can see that as x approaches 3, at x approaches 3, the function here approaches, f of x here approaches it. Okay, f of x approaches it. However, at x equal 3, f of x is undefined. So again, like I said, the value of the function at the point have nothing to do with its limit. You look at this function, f of x equal x squared minus 9 divided by x minus 3. We can factor this at x minus 3 times x plus 3 divided by x minus 3. So this function equal x plus 3. This telling us that this function here have a discontinuous at x equal 3 because of the denominator. However, the graph of the function is a linear equation. So this graph is a linear graph with it is a line that have a discontinuous at x equal 3. Okay. Now we write the limit at x approaches a of f of x and say that the limit of f of x at x approaches a equal L. If we can make the value of f of x arbitrarily close to L, as close to L as we like, by taking x to be sufficiently close to a on either side of a, but is not equal a. Okay, so on either side, it is as close as possible, like we see here. Then L can be as close as possible to this value, but the value at f of a may not be exit, like that previous problem that we had. Again, the limit of the equation have nothing to do with the value of that equation at that point. Find the limit of the following function. Find the limit of the following function for f of a at x equal 1 and the next one at x equal 1. They both at x equal 1. Okay. At x equal to 1, the limit as x approaches 1 of f of x is equal to 0.5 from both sides at x approaches 1 from the left and at x approaches 1 from the right on both sides at as close as possible. The value is approaches 0.5. The limit at x approaches 1 in this case, f of x, is also equal to 0.5. Note that the value at f of x, the value of f of x at x equal 1, f of 1 is equal to 2 here. It has nothing to do with the limit, right? The limit here equal to 0.5. And like we said, the limit of the function does not depend on how the function is defined at the point being approached. And that is a very important point that you have to keep in mind. Discuss the behavior of the function at x approaches 0. So here at x approaches 0, as x approaches 0, well, the function is f of y is approached 0 on the left, okay? At x approaches 0 from the right, y approaches 1. In this case, as x approaches 0 from the left, y approaches negative infinity. At x approaches 0 from the right, y approaches positive infinity. Here, because the function is as x approaches 0 from the left, we can see that y is approaches 0. But at x approaches 0 from the right, we can see that the function is oscillating here. So we don't know exactly what value here we're looking for. So we don't know. So then y does not exist. Okay. Now, in this case, this leads us to, as we were looking at this problem, as you can see that I'm talking about the limit from the left and the limit from the right, right? So let's go ahead and define one-sided limit. We define two types of one-side limit, the limit from the left and the limit from the right. The limit from the left is the value that the function approaches as x approaches the value from the left, and the limit from the right is the value of the function as x approaches the value from the right. And repeat one-side and two-sided limit. If the limit is equal to L, if the left side limit equal to the right side limit. So let's take a look at this example. Given a graph, and let's see what happened with the limit at x approaches negative 3 to the left. As x approaches, at x approaches 3 to the left. At x approaches 3 to the left, f of x is equal to 0. It's about 0. Approaches 0. The limit at x approaches 3 from the right side is, we're talking about this portion of the graph, and this approaches negative 4. This means the limit at x approaches 3, 3 does not exist. Then we can decide whether we take in a 0 or negative 4. So this here we have a jump discontinuity. So this is called a jump discontinuity. We have a jump here. At x approaches negative 3 to the right, we have this value negative 5. At x approaches negative 3 to the left, we also have negative 5. Is it right? At x approaches negative 3 to the left. Oh, this is a typo. We want to look at the limit at x approaches negative 5 to the left, and x approaches negative 5 to the right, and x approaches negative 5, and a value at f of negative 5. At x approaches -3 to the left, at x approaches -5 to the left, okay, we are looking at this value that is -3. -3. This means that the limit at x approaches -5 is equal to -3. The value of f equal -5, here we have a hole. This does not exist. Use the graph of the function to estimate the following if possible. Okay. So let's go ahead and plot this on the graph, and we go ahead and use decimal. So our first function is absolute value of x squared, what was that again? X squared minus 4 divided by x minus 2 minus 4 divided by x minus 2. Let's double check. Alright. And we want to find the limit at x approaches 2 from the left and from the right. As you can see here, according to this function, the limit at x approaches 2 from the left is equal to -4, and at x approaches 2 from the right is then equal to +4. So according to our graph, this function becomes -4. This approaches 4. Therefore, this limit does not exist. Well, let's talk about the infinite limit. What happened with that? We define 3 types of infinite limit. Infinite limit from the left, f of x. Let f of x be a function defined at all values on an open interval of the form BA. If the value of f is increasing without bound as the value of x where x less than a approaches the number a, then we say that the limit at x approaches a from the left is positive infinity, and write the limit at x approaches a from the left of f of x equal positive infinity. So you can look at this then. So let's say at x approaches 0 from the left, the function itself here approaches infinity. And negative infinity. Now at x approaches 0 from the right, the function f of x approaches positive infinity. Okay. And we see that. We can also have two-side limit. Let f of x be defined for all x not a in an open interval containing a. If the value of f of x increases without bound at the value of x where x is not a approaches the number a, then we say that the limit at x approaches a is positive infinity, and we write the limit at x approaches a equal positive infinity. So let's go ahead and we use decimal to sketch the graph of the following function and discuss the limit at x approaches the vertical asymptote. Alright, so what is the vertical asymptote in this case? Well, the vertical asymptote is x equal 3 in this case, right? So let's say what happened for the limit at x approaches the vertical asymptote from the left, and the limit at x approaches the vertical asymptote from the right. So again, let's go ahead and try with our decimal. So 1 divided by x minus 3 to the 4. And as you can see, here at x approaches 3, this is the vertical asymptote. Let's draw the vertical asymptote. At x approaches 3, the function itself increasing without bound. Okay. This means as x approaches 3 from the left, the limit approaches positive infinity and positive infinity. This concludes that the limit at x approaches 3 of f of x equal to positive infinity. In our next case, we have the vertical asymptote that x equals 1. And we want to see what happens for the limit as x approaches 1 from the left, the limit at x approaches 1 from the right, and the limit at x approaches 1 of f of x. So again, we go ahead and use our decimal. And let's go ahead and put in our vertical asymptote. As you can see here, as x approaches 1 from the left, the function approaches negative infinity, and for the other one, it approaches positive infinity. So then the limit does not exist at the vertical asymptote. Okay, let's define a vertical asymptote. Let f of x be a function. If any of the following conditions hold, then x equals a is the vertical asymptote of f of x. The limit as x approaches a from the left equals positive infinity or negative infinity. The limit at x approaches a from the right equals positive or negative infinity. And the limit at x equals a is equal to either positive or negative infinity.